Hey meteorites, Mr. Music, welcome back. Today we'll be discussing taking climate data, temperature and weather, precipitation data, and doing some basic analysis. And then we'll also be talking a little bit about how to graph that onto what was called a climograph. Okay, so the data in front of you is climate data from Charleston, South Carolina. I recently visited Charleston, had a great time, so I thought I would use Charleston as my example. So the data in front of you is temperature data and precip data, and you can see the means for every month. And so if you're looking at that, I'm going to ask some few questions, and so you can hurriedly find some answers. So first question is, how many years of data has been calculated here for temperature and precip climate data? So how many years of information is there? Number two, what is the coldest month on average in Charleston? Number three, what is the wettest month in Charleston? Number four, how many months are over 50 degrees Fahrenheit in Charleston? And lastly, what is the average monthly precipitation in Charleston? And if you have to, go ahead and stop the video to do your calculations and then turn it back on and I'll give you the answers. Okay, so the answers. How many years of data? It's 30. If you look at the bottom of the graph, bottom of the chart, it says taken from 1971 to year 2000. So 30 years worth of data. The coldest month in Charleston is December. The wettest month in Charleston is August. How many months over 50 degrees Fahrenheit? That's 11. And the average monthly precipitation in Charleston, a little bit of a curveball. You want to take that 51.3, I think it says there, inches of total precipitation and divide it by 12. So you wind up getting, what, 4.2, 4.3 inches of rain. Okay, and part two of this is taking that information and plotting it on what's called a climograph. And you will see this again at pretty much every invitational. Either have to read the climograph and pull information from it to answer questions, or possibly even creating a climograph based on data. So it's called a line bar graph. So you have the green precip with the scale on the left, and make sure you use your inches, and then on the right is your average temperature in Fahrenheit, and that's your red bar graph. So just taking a kind of a quick snapshot, it can give you rain and temperature throughout the year. You can kind of see what the dry times of the seasons are, what's the wettest time of the year, the fluctuation in temperature, and almost again, hey, when would be a good time to go on vacation? Should I take an umbrella? Is it going to be really humid there? Does it snow? So that's a climograph. More to come. Okay, so the next slides are actually going to be, we're taking a little trip to the Hawaiian Islands. And you would think that pretty much in Hawaii, at least at first glance, that the weather is pretty much the same wherever you go in Hawaii. At least I did. So, first climograph is of Hilo, which is on the Big Island. And just taking a quick look at the climograph, what can you gather from that? Well, hopefully you're looking at seeing what the temperature is. And you know what? Temperature is pretty constant. No matter what time of the year you go, it's going to be someplace in the low 70s. Maybe up to, low to mid 70s every month all the way. So really consistent temperature. But then what do you see about precipitation? It rains a lot in Hilo. A lot. Wet. Very tropical, rainforesty kind of a feel. So, now go to Honolulu, another island in Hawaii. And what can you see from there? You know what? The temperature is about the same. And one of the reasons why is you're basically surrounded by water no matter what island you're on. And so, again, we talked about how water and being close or surrounded by large bodies of water kind of regulate your temperature. So temperature doesn't really fluctuate too much. Doesn't ever get really cold because the water's always staying warm. And but here we go. Honolulu, it's very dry. hardly any rain at all, particularly relative to Hilo. And so I'm going to ask you a question: is why is that? All right. So here's a slide now of the actual Hawaiian Islands, and you can see where Hilo is there on the far right edge of that slide, and then Honolulu kind of in the middle. Well, if you look at Hilo, Hilo is on the eastern edge of the island, and the trade winds are actually coming from east to west, and I'll show you the Hadley cell in the middle. So unlike where we live in North America, most of the places in North America where weather is impacted by the westerlies, winds coming from west to east, because they're in the Hadley cell or the trade wind area, their winds actually go from east to west. So being on the eastern edge of a body of land next to a large body of water is actually the windward side of the island. So they're getting all the moisture coming off the Pacific, and that's why Hilo gets so much rain. If you look at, when we look at Honolulu, it's on the southern side of their island, and it also has a mountain range to its east. So it's basically on the leeward side of the range, even though it's on the west side, because it's the trade winds and the winds are blowing from east to west, it's considered leeward. So that mountain range and the southern exposure actually make it a lot drier, and that's why Honolulu is way drier than Hilo, even though they're both the Hawaiian Islands. So here's your 3-cell model, also known as the Hadley cell, even though there's 3 cells. If you start at the equator and you go north from the equator 30 degrees, so from 0 to 30 is the Hadley cell. And the primary wind belt within the Hadley cell are what are called the trade winds. If you can see, normally the surface winds of the Hadley cell flow from north to south, but because of the Coriolis force, the spinning of the earth, everything in the northern hemisphere bends to the right. So those north to south surface winds actually bend and become out of the northeast to the southwest. And that's the wind belt that the Hawaiian Islands are in. So therefore, that's why the prevailing winds are coming out of the east. Now, where most of North America weather lies within what's called the Ferrel cell. That's the middle cell. That's the cell between the Hadley cell and the polar cells. And those are also in the southern hemisphere as well, as you go from the equator to the poles. The Ferrel cell surface winds, as you can see, actually move from south to north. So again, moving south to north, put a little right-hand bend in it, they actually become called the westerlies, so they're coming out of the southwest, going to northeast, and that's why most of our weather here in North America travels from southwest to northeast. And then you have the polar easterlies, those 60 to 90 degrees up top. So that's your 3-cell model. That really drives the major winds. And we'll talk about that more as the year goes along, because getting into the Hadley cell and the trade winds has a lot to do with El Nino as well. And we haven't even got there yet, but we will. All right.